recording. Let's see, where is my cursor? There, okay.
I wonder if they just swapped up there.
Yeah, I left a note up there. He shouldn't be waiting because I think he'll read the note. But all right, so first things first. We'll just talk a little bit about syllabus, and then we're just going to go through the exam questions just to review how reactions work. Because if you remember me saying the number one things, the first reactions we're going to add are basically undoing elimination reactions. So they follow very similar mechanisms. So we're going to start by doing our exam review and just going through the exam problems. What's SN1, SN2, E1, E2, that kind of thing. And then the new material we'll get to today. This is actually the first time I've ever taught this class where we didn't have a snow day in the first week of class. So I actually have an extra lecture day to play with. So instead of so we'll do our lab slides are going to be the second half of today's lecture, and then which works out nicely because I have to pick up my son and get him to basketball practice at the Kale Community Center by 4. So that was going to be tight if we went till 4 in lab.
Right.
Hey, David.
Sorry, room switcher.
Yeah, no worries. You saw my note. I figured that's why I left the note there. So we'll talk about mass spec today. So we'll end our exam review by talking about NMR and IR because that was the last stuff on the exam, and then we'll go right into a new instrument called mass spec, which it's still considered a form of spectrometry, although I'm not sure why, because it doesn't involve light at all.
Because isn't it more or less just finding like molecular weight?
Exactly. It's basically, it just breaks everything up into small pieces, and then you can measure how much the pieces weigh. And we'll talk about some of the theory and how to interpret some of that, but that's all your lab is today. So then once we're done with lecture today, I'll print out the labs. It's just basically define these terms, do some practice interpreting. So it's a pretty mellow first week. And then on Thursday, we'll get into addition reactions and alkenes in more detail. We've already talked about naming alkenes, but we'll get into how they react as well. But first things first, just to go over the syllabus. I just hit publish on the course on Canvas. And I'm still finishing up the syllabus. And as you can say, we have a random TBA day first week because I'm not used to having 2 lectures this first week because of snow usually. So we'll make use of that this week. But it's pretty similar stuff. Got a schedule right here. We, as usual, especially in the second quarter of a 3-quarter class, if we have some wiggle room, as I recall, last year we didn't get past chapter 16. And actually for this one, and actually I need to update these chapters because this is still for the old textbook. So the chapter numbers will change a little bit. The material doesn't, but just where it is in our OpenStax textbook will change a little bit. But we probably won't get through past the Diels-Alder. These 2 material, or there's also another class of Diels-Alder reactions called electrocyclic reactions that are entirely orbital based and talking about highest occupied molecular orbitals and lowest unoccupied molecular orbitals. And so that's going to be a little bit of review, and it's a little bit tricky, but it's kind of cool because this is one of the places where you can see the quantum actually makes a difference in. What we'll see is with some of these Diels-Alder reactions, if you catalyze it with heat, you get one product. If you catalyze it with light, you get a different product because the light works by exciting the electrons to the lowest unoccupied orbital, but heat, you're using the highest occupied orbital. So something as simple as, do you use light or heat, will give you the cis versus the trans product in that case. So that's a fun chapter, and I kind of like to spend time on it because we put in the time with orbitals in my classes. So, but all the rest of this is pretty similar to what we've seen in the past. Paper lab this week. will be, next week we'll start doing, wet labs. And then this is all sort of the boilerplate stuff. I've updated everything. You all know where my office is at this point. We're all these three rooms, my office, this classroom, and our lab are all right together. So nice and inconvenient. My office hours are still 9 until 10 on Tuesday, Thursday, and 9, 10:30 on Monday, Wednesday. But anytime you can find me, unless I'm in a meeting, feel free to ask questions. I spend a lot of time actually in the lab, because on their ICA days, their in-class assignment days, they usually just come pick up their assignment and leave. And so I'm just kind of hanging out. So Monday, Wednesday mornings are also a good time. From 10:30 to 1, basically, you can usually catch me around if you have any questions. The last few things I have to just update the textbook, and then I'll be able to upload this to the Canvas shell. This hasn't changed. I think this is the same makeup as it was last quarter. 30% quizzes, 30% assignments, 30% exams with a 10% final lab report. The lab report will be a little bit different this time because it'll be a synthesis proposal. Instead of here's your unknown, what is it? It'll be here's what you're trying to make, and I'll give you a spreadsheet stock room, and you'll be able to go through and say, okay, starting from anything on this stock room, how do I make my product I'm trying to do it in as few steps as possible. And then you actually have to propose, like, I don't expect you to get it perfect because it'll be your first time writing a procedure from scratch. But it'll be like, okay, take this many grams, take the, all the way out to writing it out, how you would go into the lab and try it for the first time. So that's kind of a fun lab report. It does take a little bit of work. And just like with last quarter's lab final, everybody will have their own unknown they're trying to make. So that makes it easy because you can work in groups to kind of troubleshoot together, figure stuff out, and then write your own procedures. And so there's that usually works pretty well. I think everybody enjoys that. I think the rest of this is pretty. I gotta update these dates too. But it's all my standard syllabus. You guys are second year students at this point. Don't need to give you the spiel about, if you show up ready to pay attention, don't screw around, that kind of thing. And we do have the recordings too, right? So, especially for this winter quarter, don't get yourself into a wreck trying to make it here in bad weather, right? These recordings in this classroom aren't going to be quite as good as the ones where we had the smart board, but they're still going to be legible. Still be able to take, it'll capture everything from the webcam there, and capture all of the board work relatively well. So don't hurt yourself. Don't get into an accident or get stuck on the side of the road trying to make it here. If the weather's bad, just let me know or don't, and just use the recordings to make it up.
I think we'll let you know not this week, but next week on this Thursday.
Okay, cool. Well, you know the drill then. You know where to find the links. It should be fine. There's my cursor. Any questions or I'm open to suggestions on my syllabus. I'm always I think everybody that made it through OChem 1 figured out how to work my system and everything, make your resources work for you. But feel free to talk to me in office hours if you have any private concerns or suggestions. Always looking to keep it from getting stale.
Just
A few jokes. Yeah, exactly. We can be pretty flexible, right? All right, well then we'll jump right in then and start talking about the exam questions. Try and remember where everything was. Kind of how I do. Gen Chem 2 does the same thing. We start by going through the exam from Gen Chem 1 because there's no better way to review than to remember what we decided was the most important stuff from Gen Chem 1 or OChem 1 in this case. So what are our I do have some so the first part of the test was draw all possible substitution elimination products. So that that meant we were talking about all four of our mechanisms, which were, give me one, E1, E2,
SN1.
SN1, SN2, bingo. All right, so which one of those is gonna have the fewest possible products? That's the one I like to start with, it's the easiest one.
Yes,
SN1, we gotta worry about.
Oh,
arrangements
sorry.
though, right?
SN2.
SN2 is only gonna give us one product, right? If we wanted to draw the mechanism, it would look like. This, right? So. We have our nucleophile attacking, a partial positive, our leaving group leaves at the same time, so only one product, right? Nothing changes with the ethyl group. And we have that backside attack, that backside displacement. Which means we're gonna chlorine leaves going into the board, which means our ethoxy group attaches coming out of the board. And so for SN2, that's all we have to deal with, just the one product. And in general, we tend, the second order reactions tend to have fewer products, right? Because they're concerted, there's no rearrangements you need to worry about. If we're gonna look at E2, then it's not, so we'll label this. If we're gonna do E2, it's still gonna be concerted, right? Which means we still have our leaving group leaving at the same time, except it's not gonna act as a nucleophile, it's going to act as a. What's it gonna do for an elimination reaction? It's gonna act as a base, bingo. So it's gonna pull a hydrogen off of one of the adjacent. So we have a hydrogen here. Hydrogen here, hydrogen here. I mentioned this to Zeke earlier. I grabbed the wrong folder this morning. I have your tests that I'll give you back with your scores and everything on Thursday. I just left them at home this morning. Which is actually okay for this part because I don't want you just going back to your test. I want you to think about it fresh, right? So where are we going to see this base pull a hydrogen off? Any one of those three gonna be more likely or less likely than the others?
More likely, less steric.
Less sterics. And plus, remember that for the E2, we had that anti-Curry planar requirement, right? So if our leaving group is into the board, we can only pull off a hydrogen that's coming out of the board. Which means these two are basically off limits.
Yeah.
So we actually are only gonna get one E2 product as well. Okay, so we'll have. Three arrows this time, so leaving groups leaving, our base is pulling a hydrogen off, and the hydrogens, electrons are moving over to make a pi bond. And so that'll give us this product. Right, and it actually, in this case, it's not actually gonna make a difference whether it grabs either of these two hydrogens, right? We get the same product either way. But in this case, we're not gonna see anything, even though it's the more substituted product, which that's a Z7 where we would normally expect to see more of the pi bond right here. But not in this case because we can't, this ring structure makes it so we can't freely rotate. So we can't put this hydrogen opposite of the board. If this wasn't a ring structure, we wouldn't be worried about that. So as a ring structure, we'd be able to rotate this so that the hydrogen was coming out, and then we'd still be able to make that more substituted product. But because of the ring structure, that creates what's called a hindered rotation or a restricted rotation. Even though these sigma bonds we would normally be able to rotate it around however we want, the ring structure prevents that. So then here's our E1. Sorry, E2. And then the SN1 and SN and E1, the two stepwise reactions, we're gonna get everything, right? We're gonna get a bunch of different products. The key with those was remembering that you've got that rearrangement that can happen. And just since we haven't tried it yet. Yeah, you'll be able to, I think you'll be able to see that on the recording just fine. It won't be. It's mirrored here. It actually, in the recording, it unmirrors it. All right, so if we're doing SN1. Then that means we start with leading group leaves. And we get that carbocation, right? So I'm gonna switch colors and do it over on the right hand side here. So we'll have this at first,
And you have the rearrangement.
and then you have the rearrangement. So our actual intermediate that we're drawing our products from is gonna look like that. And just a reminder that those carbocations are trigonal planar, right? They turn into sp2 when you have the carbocation. So we don't have into the board and out of the board anymore as soon as we do that rearrangement. Which means that for SN1, we still have our nucleophile coming in and attaching, but we're going to get it attaching to the tertiary carbon. And do we need to do an R plus S here?
Perhaps someone. Normally does.
Normally, yes, but because both directions around the ring are symmetrical,
There's no point.
there's no point. And I'll give David a shout out here. You are the closest I've had to a perfect test in this class.
I saw.
And the only point that I took off was because you wrote R plus S on something that didn't need it. And I let it go the first time, but you did it twice.
Oh, gotcha. Fair enough.
But
I'll take it.
I was very impressed. Nice work.
Thank you.
All right, so then if we go E1 from the same intermediate, the nice thing about the stepwise reactions is they're gonna go from the same intermediate. So then our elimination product here, we have 2 alpha carbons, but they're both symmetrical. Actually, technically we have 3 alpha carbons. Right, so we're gonna have, but these 2 alpha carbons being identical means they'll both give us the same product, right? Doesn't matter if our base pulls a hydrogen off here or here, it's still gonna give us that product. The last alpha carbon is up there. And that's gonna be, would we expect this one to be more likely to be? I guess, let me draw the product first. So which of these products would we expect to see more of? This wasn't part of the question, but why?
Because it's more substituted.
More substitute, we have 3 substitutions out of 4 versus only, or I guess this is also 3 out of 4.
Oh, it is.
So they are equally substituted. I was thinking the same thing. It seems more substituted.
Yeah.
Well, so it's not an aromatic unless we have more conjugated pi bonds. So just because there's a pi bond in a ring doesn't make it aromatic.
Right.
It's, so actually we'd expect these to be about the same.
Yeah.
Because it's deceptive, it really looks like that.
Yeah.
It's in the brain,
2,
we're
3.
supposed to-
Oh, yeah. No, I can see it now. Okay.
I even did it when I was giving you the lead up. That wasn't supposed to be a trick question. I convinced myself to until we counted them. All right, so that's the gist of what we covered for those first 2 problems, right? Was just, here's your 4 mechanisms, draw the product of all 4 mechanisms. You didn't have to draw all the detail or show the arrows to get credit for them. But for my money, I think it helps, especially when we're doing these simple mechanisms. Some of the mechanisms that we'll see even as early as Thursday are considerably more complicated. Multiple steps, lots of arrows in each step. we're gonna involve mercury, we're gonna start involving metals
Catalyst.
as catalysts. And those mechanisms, you might not want to show every step because it'll wind up taking you more work. It'll be more work and there's more places to screw up if you remember the net results. But for these mechanisms, these are pretty straightforward. So it's a good practice to show them. Any question about these ones so far? All right, well, let me clear the board. And I'll give you all a head start before I start writing them out for the second one. Repetition is our friend, right? There was anybody remember who Chad Ochocinco was? He was a wide receiver who legally changed his last name to be Ochocinco because that was his nickname, and the NFL wouldn't let him put his nickname on the back of his jersey unless he changed his name. Right. He made famous, or at least made known to me, a quote. It's, you don't practice until you get something right, you practice till you can't get it wrong. So we will continue to go follow the lead of the poet Chad Ochocinco. And keep practicing these. I think he's actually doing commentary now. I think he might have changed. His last name was Johnson. I think he changed his name back when he retired. It was literally just so that he could put Ochocinco on the back of his jersey. You got to respect the commitment to the bit, right?
Quick question, I wasn't married.
That would have been cruel. I have no idea, actually. All right. So once again, let's do SN2 first. Trick here also, when I don't explicitly lay out which one is the nucleophile, remember your nucleophile is going to be the one that's got the negative charge. And when you have more than one atom that's part of that, it's the part of the molecule that has the strongest negative charge, either the full negative charge, or if you're dealing with partial charges, it's the part of the molecule that has the most partial negative, the largest partial negative. So for instance, if we're using water as our nucleophile, I don't know that I ever explicitly laid this out last quarter. I just kind of assumed everybody got the point of following the partial charges. The oxygen has the partial negative here. So it's the oxygen that's going to act as a nucleophile, not the hydrogens. So for this molecule, sodium amide, it's not the sodium or the hydrogen, it's the nitrogen that's got the negative charge. So the nitrogen acts as the nucleophile.
It's through the reaction and the sodium kind of dissociates off.
Basically, yeah, if you can look at one of your reactants and identify it as an ionic compound, you can just pretty much always for OChem split it up into its constituent pieces. So mine's gonna come in. I'm gonna draw that on the other side, so there's our SN2. This was a simpler molecule, right? Although we do still have stereochemistry to pay attention to. And then technically, if we were balancing everything out, we'd be making sodium bromide as well. But organic chemists famously don't actually balance their reactions. Well, that part's not organic, we don't care about it. It's just also there, but don't bother. And I do that when I'm grading too. I was looking for this. I did not grade anybody down if you didn't write plus sodium bromide. It's not one the reaction, right? Then if we're gonna see E2, now once again we have two distinct alpha carbons. And both of these alpha carbons, we don't have any hindered rotation. Both of these alpha carbons have more than one hydrogen, so we're not going to have to worry about the whole anti-periplanar thing. Remember, that was really only winds up being a big deal if you have either only one adjacent hydrogen, Or if you have a hindered rotation, then you need to pay attention to it. We don't have that here, so it makes it easy. So we're gonna get. Any other?
Also, the
Bingo.
set side cement.
Because I always instinctively make them a straight line, I always tend to forget to draw that, because it looks more awkward, it takes up more space on the page that way, right? So can't forget that. That is the big difference between, so before the renovation, does anybody took classes here before the renovation? Or COVID?
I think I might have took like one or two in this area. I think it was like a technology wing, like
So, yeah, back over there where my
the
office is now,
computers.
and there was a computer lab down there too.
Yep.
But the hallway used to go where that door is, went that way. And then there was, my office was right there where Mariola's prep space is for the.
I remember the hallway kind of cut through this room.
It did, so this was basically, instead of the hallway being there, everything was shifted like 10 feet that way. And that meant we couldn't hear anybody, that when they were, you had to be pretty loud in the science comments for this classroom to actually hear them. Having the door right there, hear them a little bit more, but I'd like to see the space used, so. I'm not gonna kick them out or anything. All right. Any rearrangements we need to worry about for the second order? We gonna get any different mechanisms for SN1 or E1? Any different products, I mean? What do we get that's different?
Oh,
Yeah, we are gonna
R
get,
plus S.
for the SN1, we will get. A little bit of this. Oh, not.
Just because
equal
there's
amount.
Carlos.
Right, because when your leaving group leaves, and that becomes trigonal planar, now our nucleophile can attack from either side, so we'll get both of them. But E1 is not gonna give us any different, we still have the same two alpha carbons, the same hydrogens that can be pulled off, so. This one was actually a simpler. Simpler question, because you only have those 5 products. All right, questions? I'm gonna have to make my slides a little bit less dense. But I can do this stuff. Couldn't do that before because. Because it actually won't actually write on, do the notations on PowerPoint when you're zoomed in. Which I'm not sure what the point of that is, but. Either way, we had this side and I added our other sterically hindered base, which was the TBU, okay. Which, if you remember, that K is a potassium ion, so it's actually TBU alcohol, TButoxide minus the oxygen, yeah, so. So that molecule minus the oxygen. So it's easy to see how it's sterically hindered, right? So with that in mind, sterically hindered base means we're not gonna get the Zaitsev product, but we get the Hoffman product, the less substituted alkene. So in this right off the bat, strong base, weak nucleophile tells us elimination. Whether it's E1 or E2 is gonna be based a little bit on whether we have a tertiary or primary or secondary. Strong base, weak nucleophile is pretty much always gonna go E2. Right, even with a tertiary leaving group, because we don't need access to that active carbon, we just need access to the alpha carbons. So. That's alpha carbon, this one is less sterically hindered. So. But I guess for part one, it was just, what's your mechanism,
Yeah.
E2. And if we write the product out. There's our major product. No system trains to worry about, right? So sodium. NaSH. Blanking on what the name for that nucleophile is. Sulfahydryl group maybe? Anyway, doesn't matter. You don't need to be able to name it, know what mechanism it's gonna do, right? You just gotta be able to see it in our table. Weak base, strong nucleophile. Weak base, strong nucleophile, and it's a secondary. So SM2. Easy enough when I give you the chart, right?
Right, yeah.
But even that's the sort of thing that I expect you to understand, you know, to be able to recall. Why this is, but especially for these split cases, these middle of the road cases, I would go back and double check this too. And because there is some wiggle room on it, so it's not like.
So
after
it's
3
definitely
weeks.
E2 or definitely S.
Right. Yeah, for this column, I would expect, and this column especially, I would expect you to be able to, yeah.
Kind of just depends with the
exactly,
other little things going on.
exactly. So being able to make sense of why they are the way they are is more important than being able to have this memorized. Memorizing used to be a really core component of organic chemistry, just like with a lot of biology classes and biochemistry too. And history classes for that matter. You know,
Yeah, you can
the internet
memorize
has
stuff,
changed all that, right?
but if you can't like apply what you memorize, then it's.
Right, it's more about understanding the underlying variables, because you can always look up the specifics. I don't know how many of you were in grade school and you were taught you had to memorize all your multiplication facts, because you were taught, well, you're never gonna have a calculator in your pocket all the time.
Oh, yeah.
Oh, no, I was like beaten into my head.
Right. And what do we all have in our on our phone? We probably have like several things within arm distance that are calculators at any given point, right?
Basically a supercomputer.
Right.
I remember they were like,
So,
fastest person that can do it gets cookies. That was like
yeah, exactly, that's,
The kid that snuck behind the desk and stole it.
Oh, yeah.
don't tell me that. Cause I don't have any cookies, so you stay over there, leave my coffee alone. As someone who really enjoys trivia and trivia challenges, it's really been like a detriment, the whole smartphone, and you could look anything up at any given point. Now it's like, no, don't pull your phone out just because we're having an argument about something. I want to argue with you. I don't want to go look it up.
When you had to memorize phone numbers and directions, like use your brain a lot. Now it's like everything's outsourced.
For mindless recall though.
Yeah.
Like I still know my best friend's phone number from grade school. Am I ever gonna need that again? No, but I can still recall it. All right, let's look at, let's do D before I zoom in and move down. Water. Weak base, weak nucleophile, right? All of our strong nucleophiles pretty much all have a charge with the exception of dihydrogen sulfide. So not charged, the protonated form of some of our strong nucleophiles are gonna be weak nucleophiles. Weak nucleophile, weak base means either no reaction, or if you have to pick one of them, we're gonna favor those first order reactions. Especially since it says plus heat, that tells us elimination. Secondary, especially considering secondary with the ability to rearrange,
Right, yeah.
probably E1 is our most likely. And so again, for the sake of being able to ask you what the product is, I wanted you to pick what the most likely mechanism is, even though
Instead of just saying no reaction.
instead of just saying no reaction. No reaction is not a bad answer. It's because it's gonna be real slow. Unless we really crank up the heat to the point where we have to worry about it combusting anyway. It's kind of funny, but at the same time, that is a thing that happens with organic chemistry. If we really wanted to push this reaction And we didn't want this to oxidize in
Just to
oxygen.
get to like almost the point of combustion.
No, what you do is you do it in an anoxic environment.
Oh, okay.
You basically
Like in a
seal it
vacuum?
off in either a vacuum or you flood it with an inert gas, like you do it under argon or in nitrogen.
Yeah.
Because then you can heat it up. And it's actually, it's very similar what, the process of making fossil fuels, right? Fossil fuels originally in the geological sense, they were all just organic material too, right? But when they get sequestered down away from the oxygen and subjected to lots of pressure and heat over time, you just get this goopy mess of organic compounds, but they're not oxidized because there was no oxygen around. So we can still do that in a more controlled way. But it is a headache. For the most part, we don't want to have to do this under an inert gas. Because that adds a whole nother layer of complication.
So when they use like gas for welding, so
That is one of the reasons why for certain metals, when you weld, you have an inert gas that you basically like pass over it while you're welding, is to limit the oxidation. Yeah, same basic principle. All right, let's see. You mostly see what's going on there now. So now you can't see your chart. But even without that, no charge on this, right? It's not something we would usually think of as a strong base. So weak base, weak nucleophile again in an ice bath. Tertiary leaving group substitution. SM1. Right, and so we'll get, again, this is the other place where you put R plus S. Now that I'm looking at it. Because both sides around the ring are identical, right? As soon as there's a methyl group hanging off anywhere.
Then you can call
Then
it
it's R
chiral
plus
and
S,
it's RS,
right?
yeah.
Not anywhere, not.
Yeah.
But. We're looking at just replacing that bromine with a methoxy group. And so I don't think anybody did this, but had you written it out, just methyl. You wrote it out like this. That's technically an intermediate, not the final product. Because it's gonna kick off that hydrogen. And
To make the charge
yeah.
so stable.
It's a little bit semantics to say whether it's an intermediate or the product. This is the product of the SM1. But it's not the final product because it's immediately gonna kick off that hydrogen.
Yeah.
So just sort of to have a line in the sand, so to speak, when it comes to this class. If you can do a proton transfer and make it neutral, do it. We don't, this is still considered an intermediate, for the sake of this class. Because we're gonna wind up with, just like we saw with some of the SN1 reactions where with these weak nucleophiles, you have to do that last proton transfer. There's a lot of proton transfer steps on some of these addition reactions. If you stop at any point, not do the proton transfer, it's not completing the mechanism. Which again is semantics, but at the same time, just make that your rule for this class. What we were actually looking for was that. And then last but not least. Tertiary carbon. Strong base, strong nucleophile. So it does have a charge, exactly. It's in a protic solvent, but that's not gonna make a difference in this case, right?
Solvents is kind of the last thing that you really. look at.
Exactly. And I don't, if I'm remembering correctly, I don't think it showed up anywhere on the test. One of those things where we spend more time talking about it, made it kind of blow out of proportion, if you consider the amount of time we spent talking on it compared to how much it actually matters. If you're actually an organic synthetic chemist and you forget about solvent effects, it winds up being a really big deal for your personal life for the duration of how long you forgot that. But unless you go into that field, most of you are never gonna have to worry about the solvent effects again. So strong base, strong nucleophile, but tertiary. which means we're gonna get the combination of, SN1, E1, probably. Go back,
Not us, it'd just be E2, right?
or sorry, E2, you're right. I was thinking weak base, weak nucleophile. Yeah, so we'll get E2 here. And favored product, so we have 3 alpha carbons again, the favored one, it's not a sterically hindered base. So it's gonna be. Plus the cis. This is the trans isomer. Did I do that?
This is an interesting one to draw out.
There.
There.
In some cases, if you're trying to just draw the opposite of what you drew there, it could be easier to just draw the alkene part and then just put methyl, hydrogen, ethyl, and methyl. So that all you have to do is switch those two. All right. Everybody feeling pretty good about SN1, SN2, and E1 and E2? All right. Let's. It'll come back to you. It'll come back, especially when you get, the more we keep talking about it. This is as good a time as any to take our break because we're going to do all instrumental analysis and adding a new instrument after the break. So we'll do the NMR review and IR review and mass spec in 10 minutes. Come back at 5 after. Is it, have you seen all together? It basically, I don't know where the projector is right now. And this means.
Oh, is it like a little
It's
sandbox?
an- yeah.
Play with? Oh, okay.
But they took the projector off or something. And it was totally, it's all designed and built by one of our adjuncts, just out of spare parts, basically, so.
I can tell, since they have GTX 1070, it's kind of really. It's an old fucker.
Yeah, when the camera they put on the top is an Xbox Connect. They haven't made those for 10 years, probably.
Yeah.
Yeah. Especially if you hang out for the rest of the lecture.
Yeah.
I'll print them out for everybody at the end of lecture so that everybody that wants to can head out. It's basically just some definitions and some practice with this, with spectroscopy, just because it is a very different type of spectroscopy. Let me. No. No, you put the break down left the back. I forget if they don't unlock this. I have the keys to unlock it, but since I came in that way.
Do you mind if I start taking off like 10 minutes early? I like to make it too fast. Yeah, it's like right down the street.
Yeah, no worries. You go to St. Teresa's?
Yeah.
That's not fast, is it?
No.
Temple.
Yeah.
Or synagogue, I think.
Yeah.
Temple, though, I think
Yeah, that service is called, yeah. I get it mixed up because I went to high school with a whole bunch of Mormons and they went to temple every morning too, but it was very different temple.
There's no image to that, which was just, there was St. Teresa's and then Our Lady of Top, which is like a.
Oh, okay. Zelverb and Zephyr or something, probably. Yeah.
Yeah, I think St. Teresa, they rebuilt it recently in the stained glass windows they have, gorgeous.
Yeah.
Like all over the entire room, the measurements, there's like 7 or 8 of them.
What are all these churches that are like Latter-day Saints? It's like 10 churches.
Oh,
So Latter-day Saints is Mormons.
That's
Yeah. It's, I think the Book of Mormon is the text that they study, but the church is the Church of Latter-day Saints. And then there's a Jehovah's Witness temple in town too. Christian Scientists, I think, are around. It's not what the name makes it sound like. I don't remember specifically, but I had to take a bunch of comparative religion classes when I was in undergrad, because I went to a religious undergrad. And I think they're closer to Seventh Day Adventists, I want to say, than they. Yeah. But I don't remember any specifics beyond that, other than they were one of those kind of mainstream Christianity adjacent groups.
And there's like thousands, literally thousands of denominations.
Yeah.
I don't know why. Because everyone disagrees on something.
Right. All right, so we will. I'm plugged into the projector here, but it's not connected to the network, so it won't let me print from here. So I can't print off the cheat sheet of NMR chemical shifts for the sake of doing this problem, but we can still estimate, and I have it pulled up on my screen here, so I'll throw that up as needed. And so this looks like a much more complicated molecule than the practice one, right? But it still doesn't have that many distinct hydrogens, right? Because you've got 2 here, 2 here, the aromatic regions, which
It's only 4.
is only 4, and it's symmetrical.
Right.
And then 2 and 2, well, 2 and 3, but as far as counting the number of signals, we should have 1, 2, 3, 4, unless you count all of those as one signal, which would be fine as well. And then 5, 6, so it's a total of 6 signals. And. This is definitely one where to split hairs about where they're gonna show up in the. Chemical shift. For 1, 2, and 5, and 6 in particular, for 3 and 4, we know where those are gonna show up, right? They're gonna show up between 6.5 and 7.5, because that's where aromatics always show up.
It's kind of just gonna be a mess.
It's gonna, and it might be a mess, but because of this, how much symmetry there is here.
You could probably see the peak a
It'll
little more
probably
than
more
one,
like
yeah, like that.
where with an integration of 2 and an integration of 2. If this wasn't completely opposite, if this group was right here, then it's a mess, because now you have 1, 2, 3, 4 that are all chemically distinct from each other,
Right.
all showing up at the same point.
Fun complex splitting them.
Exactly. So that's when we would really expect the aromatics, when this is what's called the para substitution, when they're completely opposite from each other. Generally, you tend to get a little bit neater. Chemical or splitting with the aromatics that way, but I wasn't really grading, if you just threw it as a big mess, that was fine for this class, because that's how we practiced it. We're gonna get into that in more detail when we spend more time with aromatics. In later on in the quarter. So. And really, we probably would wanna go back and double check that the methox, or that the oxygen directly attached, or the chlorine directly attached to the carbonyl. Is not gonna throw it off too much. And I did give you a fairly detailed.
I think there was mostly everything wrong.
Yeah, if you look, you can find just, so here's a carbonyl group. With carbon directly next to it, and it even specifies a ketone versus an ester versus a carboxylic acid. This is mostly what we're looking for, right? So that's an aldehyde. Aldehyde or a ketone, both is still gonna put it between 2.1 and 2.4. So not anywhere near the aromatic region. And then a chlorine directly attached to a carbon, that's 3.1 to 3.4, still upfield from the aromatic region. And then somewhere on here there's an alcohol. The ethers are on here too somewhere.
I remember having a hard time looking for the.
Yeah, it's gonna be,
I
close, so there's the alcohol. Oh, this is the ether right there.
Yeah.
So RO carbon, so still 3.2, 3.8. So deciding between these two, these are gonna be the chlorine versus the one directly attached to the ether. Those are gonna be close to the same. I wasn't picky about what order you put them in. They're both in that 3 range, so. Let me go back to the structure. And these, direct next to it, and then this is just gonna be treated like a regular methyl, basically, so down between 0 and 1, basically. So 6 signals, these ones both between 3 and 4, either order would work. So let's start with the furthest downfield, because I like to work from left to right. So our furthest downfield is gonna be our aromatics, so 6.5 to 7.5. Integration of 4 for the whole thing, right? By being really careful with how it would actually look like that if we actually plotted the integral, because it would jump up here and here, and then be relatively flat and jump up again here. But again, wasn't being picky for the sake of this. This was all about getting qualitatively right. So that takes care of 3 and 4. What did we say for adjacent to a carbonyl? 2 something, I think we said. Yeah, 2.1, 2.4, so we'll do those ones last. So this is gonna be carbons 3 and 4, C3, 4. And then we'll have something for carbon 1 or carbon 2. I would typically put carbon 2 as being more downfield. Because that's basically a methyl group, and methyls are usually shifted to the right a little bit more than the rest. And oxygen is slightly more electronegative than the chlorine. So if I'm splitting hairs, which you probably were at this point when you got to this part of the test. We would do 2 first, and it should have an integration of 2 as a triplet, because that has 2 nearest neighbors. It has that n+1 rule, right? So this is carbon 2 around, call it chemical shift of about 4. Just doing my integral signs weird today. And integration of 2. Carbon 1. Call it 3.5. Also 2 nearest neighbors, so triplet, also an integral of 2. And last but not least, we've got 5 and 6. 5 is going to come first. Integration of 2. What's the splitting going to be?
For 5?
For carbon 5, yeah. Yeah, so 3 nearest neighbors. So we'll see the quartet. And it's gonna be in that 2 to 2.5 range. Last but not least, C6. Integral of 3, 2 nearest neighbors, so another triplet. Right, so there's a lot of background in looking up numbers to get something fairly qualitative. But you know, it's one of those things where if you know what you're looking at and what that table of chemical shifts mean, it's not totally out of left field to be able to get here. Especially the more time you spend with NMR, the more it's going to start seeming like second nature. You know, just like with a lot of chemistry concepts, it's kind of like learning a second language. Once you get there, though, it's pretty okay. I understand the logic. It's very methodical once you put in the time.
Oh, we're just diving deeper into already broken language.
Right. It's true, yeah. Starting from English and then working through chemistry from English is probably the relatively tricky too. Although you should be thankful that we're not doing this in Spanish, because Spanish, as much as it's a better language than English for a lot of reasons, they still do all of their science in English. So we'd be doing some sort of Spanglish chemistry where we're talking in Spanish, but then using English terms to talk about chemistry. It'd be more layers of abstraction because, yeah, for better or worse, English is the common language of science, pretty much across the board. Even people that think and speak other languages that do science, they still have to publish in English. Which actually, that means that there's a career path. A friend who works at the college, her brother is one of the only biliterate geologists who speaks and writes at a technical level, Spanish and English. So basically he takes Spanish speaking research labs research and their papers and translates them to English for publication. And there's very few people that have that set of skills. So that's actually his career path, is actually technical translating of geology for science journalism, which is kind of cool. You could go into that field. What's that?
And every paper is different.
And every paper is different. Yeah. Yeah, you get to come in, learn some new things, talk to some new people, get paid a consultant rate out of their grant money, so they don't care. So yeah, it's yeah, and there's a lot of room for stuff like that. Because there's a lot of science going on in other places than just English speaking countries these days. Yeah, I guess especially, yeah, there's a lot of research. Russia is not as prevalent in in chemistry research as it used to be, but I'm sure that there's still stuff going on. China's putting out a ton of stuff. And to be honest, they're publishing more than they're actually researching. They're publishing kind of garbage that's poorly translated and it's not really good
No, there's-
science, and some
yeah,
of it's
there's
just
a lot
fake
of, like,
data,
Biochemistry journals from
Mhm.
China that are kind of just like
real sketchy.
weird. Like,
Yeah.
I look at them.
It's like, a lot of the best papers I've read are by Chinese people.
There's a lot, yes, so I don't mean to be
Yeah.
dismissive of Chinese science as a whole, but they're putting out a ton of volume. And while some of it's very good and very relevant and going to is groundbreaking, there's a lot of it just kind of.
Yeah.
The Chinese journals have not implemented the same level of rigor and peer review.
Our president told us to inject bleach in ourselves, and we're talking about Chinese people with their science. I think we can take a step back.
Well, there's that too. There's that.
I ran into a funny problem, doing my thesis research for my bachelor's,
Mhm.
this one protein. And we found this, paper that was published in Nature that had like these results that we then went to use for one of our experiments. And it like didn't work, so we went back and like double checked everything, and then like, okay, and then tried it again and it still didn't work. And then we went back and like, we tried to replicate their results and like they just blatantly lied.
Yeah.
It's in Nature.
Yeah, there was,
Kinda crazy.
there was, when I was in grad school, there was a really big deal. There was the current hot topic research in chemical engineering was molecular components. They were trying to design single molecule circuit components, like a transistor that was just a single molecule.
Say about this.
And there was this one research lab run by one investigator, they were the groundbreaking. They were publishing like 80 papers a year on this stuff in huge journals. And it wasn't until somebody noticed they used the exact same figure in a totally different application. Like
That's what I
they're,
remember
and
seeing
then
it, like a
it's-
little meme.
Yeah.
It's the same figure, but totally different, like.
they just basically relabeled the axes.
Yeah.
And put it in a different paper, and then they went back and looked at all of this guy's stuff, and none of it was replicatable. And so that's career ending in science, right? So there's a lot of that's science. Academia in general right now has a lot of that going on, but that's actually one of the few places that I think that AI is actually really useful, is that AI is really good at combing through things and saying, hey, these are the same figure used in two different
It
places.
can detect.
It can
those kind of,
detect
like-
those really quickly.
Yeah.
So detecting plagiarism, AI is actually, it's ironically, both
Really
for
good.
plagiarism and detecting plagiarism, AI is pretty good. Beyond that, less so. All right, this one, I tried to fit too much on the graph for what we have here. But this was our multiple choice, basically rule stuff out, right? So here were the molecules we had to choose from. Here's the IR. You can see the details a little bit more over on the screen here. And just this. Oh, look at that.
Instead of alcohol.
So it definitely has an alcohol, so that allows us to eliminate one right off the bat, right?
SP3,
Well, SP, there's one right, there's a peak on both sides of 3,000, right?
Right.
So probably some SP3 and some SP2. Which, does that allow us to rule anything out? Yes, far right, so these two are both out,
Yeah.
just by looking at the first two things on the IR. So this is where IR is really useful. Is in terms of narrowing things down and then getting the specifics. These both are fairly similar molecules in a lot of ways, right? So this is where NMR might end up being more useful. So to decide between these. They both have an alcohol, they both have an aromatic ring, they're both di-substituted on the aromatic ring. If one of them was di-substituted and the other one had three things attached to the aromatic ring, we could just use the integration. On the aromatic ring to be able to figure that out, right? Because one of them has an integration of 3, the other one has an integration of 4. But they're both the same, they both should have an integration of 4. This isn't the approach I expected you to use, because we didn't spend a whole lot of time. This one has that para substitution though, like we talked about. So we
So it's
would,
gonna be a little more cleaner when you.
I would expect this to be a lot cleaner.
Yeah,
So it's probably not that one, since this is real data, but that isn't where I expected everybody to go. Having, actually, we probably can just use the number of distinct signals
to figure it out.
to figure it out, because we have extra carbons here.
Mhm.
So here we should have 1, 2 aromatic and an alcohol. And here we should have 1 aromatic and an alcohol. So that right there is really enough to tell us it's probably this one. And this is actually a case where I expected it to have a nice clean here, but it didn't.
But I mean, it's science, it can't be perfect.
It's not perfect every time. Probably why is because the alcohol is gonna have a lot of strong intermolecular forces with the molecules around it.
Mhm.
And that can cause your splitting to get more complicated. Again, you didn't need to approach it at that level here, but got 1, 2, and 3 integration. Plus 4 for the aromatic. This matches up really nicely, yeah, this one doesn't, just from the number of signals and the integrations, all you really needed to look at it. Alright, and so that's why it's tempting when you get an NMR and just a molecular formula to try and read the NMR first. But a lot of times it winds up actually being more helpful to draw possible structures first, especially if you have the IR. Like draw every possible structure with the given formula that has the IR helps a lot with that, narrowing it down, telling you you've got an alcohol, for instance.
And
And-
the IR tells us the same thing, because there's 2 oxygens over here on this molecule, and only 1 over there, so. This,
Ethers don't really show up reliably here. And even if it was 2 alcohols, it's hard to look at something like this and tell if that's 2 alcohols or 1 alcohol. Because the reason that you get that big broad peak for alcohols is those intermolecular forces. And that's gonna look pretty similar for both alcohols in a system.
Don't ethers kind of show up around like 1,000?
Yeah, but that's well into the fingerprint
That's well
region.
into.
And there's a lot of other stuff going on in there. So you don't rely on it, basically,
Right.
when it comes to it. You might be able to, if you know that that's your structure. And then you go back to the IR and say, oh, it's probably that one, but you wouldn't
Right.
want to look at the IR and go the other way.
for practicing these, you recommended the C Boulder website for practice problems, those were amazing.
Those are,
Yeah.
good, yeah.
Yeah.
I solved all of the problems like 3 or 4 times.
Yeah.
And it is one of those things where it's an acquired taste, and I'll acknowledge that, but at the same time, it's kind of fun when you get the hang of it, it's a puzzle. Right,
It's actually nice, yeah.
yeah, it's like a crossword where you're trying to like, okay, use the IR to figure this out, and use the NMR to figure the up and down part.
It's
So-
like a jigsaw, but you have to build the jigsaw pieces first, and then you can figure out how to put it.
Right, exactly, yeah. This was always my favorite part, especially once I got the hang of it. At first, it just felt like I was making stuff up. Which partly you're gonna feel that today when we get into mass spec, because I was introduced to mass spec before NMR or IR. And mass spec feels a lot more just like, you don't have a formula, you don't have anything like this, it's just, here's something that weighs this much, what is it?
What is it, yeah.
And so it's like, well, there's like a million things that could weigh that much, what do you mean? So I don't like mass spec as much because it feels more like I'm just making stuff up. This is fairly concrete, even though there's some wiggle room here and there.
So with mass spec, normally like when you do it in like the laboratory setting, like the computer that you're doing it with has like a database that will look at.
It is a little bit like the fingerprint region, where if you compare it to a bunch of known, if you have it, again, this is something the AI can look at. It's a little bit like in the old CSI shows, the old crime where they would like get a fingerprint and then put it into a database and it would spit out. And it's just sitting there. It's a little bit like that. They do have those databases. They're not always perfect, especially if you didn't get your sample perfectly clean, because then you have 2 things on top of each other and that'll confuse things. But that's a perfect segue into mass spec. So again, might work better to look at this screen here, because I think I didn't build these slides with this room in mind, that narrow. But basically, the way mass spec works, it's the same thing that I think I mentioned this probably, that if you've ever had your hands swabbed at TSA at the airport, they swab your hands or your bag and then they put that little cloth into a machine and then it tells you you're good to go or you need secondary screening. It's basically a really cheap version of a mass spec. It's just not very precise, but it basically is doing, it's just got a list of compounds that if you get these particular compounds show up, that you have to get secondary screening. So it can be, and contrary to popular belief, for the most part, TSA does not actually care about drugs whatsoever. That's not TSA. That's a whole different enforcement agency. They're just looking for safety stuff. Now, do they share data where they're not supposed to and don't have a warrant to? Maybe. I wouldn't gamble my freedom, my incarceration on TSA not paying attention to drugs per se. But in theory, they're not. That's not what they're looking for.
Isn't the company that funds like the DEA and the TSA, like, same company, so they do have the same.
DEA is its own, is part of the FDA, I think, and TSA is part of Homeland Security.
And it's all those three big companies that.
Oh, and the contractors,
Yeah.
probably. Yeah, there's a lot of. Just say if you're looking for a way to transport illegal materials, I wouldn't go flying them on a plane. It's not the route I would
Probably
take.
pre 9/11, you probably could.
That would have been a different story.
That would have been a different story.
It's my plane.
No, but if you have to go through security, if anything looks suspicious, they're gonna pull you out, and if they do find. If they pulled you out because they were looking for plastic explosives, but they actually find a kilo of cocaine, they're probably still not gonna let you get on that plane.
Right.
So
It's my plane.
if it's your plane,
Outside of government
That's
districts, then it's perfectly legal to contain anything in that aircraft.
I'm not gonna say that. Alright, so the way that this works, and the way that that machine in airports works, is basically you just use up high energy electrons. To basically knock an electron off of the molecule. So if you have a molecule just floating in space as a gas. They do this in a vacuum tube, so we have as few things in the way as possible. If we have, say, acetone, we fire a really high energy electron that's just straight up moving really fast. At this, there's a decent chance we're going to knock off an electron from one of the other bonds or one of the lone pairs. And as soon as you do that, two things happen. One, we made it a radical, which makes it really unstable. And two, we made it charged, which is also unstable, but the other thing that's useful about charged particles is that they react to magnetic fields. So basically, all a mass spec is fire electrons, knock an electron off of something, and then put it through a tube with a magnetic field. And then you measure how much it bends. Basically, when you expose a known magnetic field. And if you know what the strength of the magnetic field is, and if you know that the charge is a +1, you can work backwards to figure out what the weight of that fragment is. Right, because the force, who's had their physics recently, the magnetic force due to a charge is like force is in mass 1, that's gravity. It's
The magnetic
Forces.
force, I'm pretty sure is.
mass over r squared times field strength or something, right? T, maybe?
I'm pretty sure it was Tesla, it was Tesla's times the magnetic field strength times current.
Okay,
I'm pretty sure.
so all of that, if we combine all that
Current
into
relates
magnetic,
to
yeah.
magnetic.
right? If you're talking about electromagnets especially, right?
Yeah.
If we just combine that all into one term, we just call that the magnetic field. Basically just the mass is the other piece of that, right? So if you know this and you know this, we can figure out what the mass is. And so that's basically how they work. There's a lot of stuff labeled here, but this is the basic setup that for the simplest mass spectrometer. They came up with these back in the 50s probably. So it's been around a long time. There's been a lot of improvements. But basically, here's our electron beam, or these red arrows here, here's our sample, and our sample works best, because remember I told you this is in a vacuum, right? So you don't want other molecules getting in the way. Basically, when you add your sample in here, it'll just immediately evaporate into a vacuum. Because you lower the atmospheric pressure
So
around it
it's
enough,
automatically.
it just evaporates basically.
Evaporates.
So you just have this gas sample moving through here. Electrons hit your sample, knock it off, make it charged. And basically this piece is basically called a focusing apparatus, because it basically eliminates things that have negative charges. And it eliminates things that have too large of a charge. And it basically makes sure that it's kind of like a lens in terms of and a laser in terms of make sure everything is moving the same direction. It removes everything else, it kind of accelerates it, moving its directions a known amount. It focuses it, exactly. It's a focusing apparatus. So now we have our charged particles moving at a relatively known speed here. And then you just have this glass tube, this is all in vacuum as well. And it's just got this curve built into it. And the curve is set for the simplest versions of this, the curve is known. And then the magnet, though, is an electromagnet where we can vary the magnetic strength based on the current. So basically, when we do that, if we keep it a constant magnetic field, we wind up with some things get accelerated too much and they wind up hitting the edge over here. And those are the things that were too light. Things that were too heavy don't get accelerated enough and they wind up running into the wall on the other side. Things that are just the right weight, the Goldilocks weight, wind up curving just the right angle, going through an exit slit and hitting a detector. And the detector works a lot like the gas chromatograph, the GC, where it can tell you, gives you a signal that's proportional to how many moles there are. It doesn't actually tell you how many moles there are, but it's proportional to that. So it at least allows us to do say mole fraction. So then what you do is you basically scan the strength of the magnetic field. This process is ongoing. You start with a really weak magnetic field, so only the lightest fragments make it to the detector. You increase the
As the magnetic field goes up, there's different compounds that will read.
Exactly.
Okay.
Exactly. So you scan through all of this magnetic field and you get a list of here's a weight. And it's not just the molecular weight, it's the molecular weight per charge. Because if you double the charge on this, that's going to affect how much is accelerated as well, right?
Yeah.
So we actually report it as mass per Z. Z is charge. So as long as your charge is +1, the number that you get out is just going to be the mass of that object. And for the most part, almost all the fragments that we're going to see are going to have a +1 charge. Very rarely do we actually see something with a +2, but it can happen. All right, so then what you actually get from the detector looks like this. Because it doesn't really matter what the piece is, what the atoms are that make up the ion, it just matters how much the ion weighs per charge, right? So you basically just have a list of set masses that your electromagnet looks for. So for mass of 1, there's a set charge on your electromagnet, mass of 2. And so you don't get a spectrum, it actually is a set of discrete numbers. So it looks like it's not spikes like an NMR where everything can kind of run into each other. It's either 27 or it's 28. Because we're dealing with integer numbers of nucleons and all of your nucleons weigh the same basically, right? Neutrons plus protons, it's going to give you the same number. It doesn't matter if it's 12 protons and 15 neutrons or the other way around, it's going to give you numbers really close to 27 either way, right? And so we get a discrete set of numbers out of this. But
But the mass over charge, because the charge is usually just +1.
Charge
So
is
it's
generally
just-
+1. Yeah,
It's just mass.
exactly. Exactly. It's we to dot our i's and cross our t's, we have to say mass over charge. But for the most part, it's always going to be a +1 charge. And so The other thing that happens though is we don't just wind up, let me go back 2 slides. We don't just wind up with this molecule as an ion. We also, because we made it free radical as well, it's pretty unstable as well.
It's gonna split off.
So it's basically fragments into a bunch of different pieces. And so that's what we actually get here. For one compound, we get a bunch of different fragments. And the way you can think about this is it's a little bit like if you built a model airplane out of Legos, and then you hit it with a golf ball really hard. You could probably still look at the pieces and figure out that it was a plane, right? But you're not gonna just knock off one piece and do that.
Right.
You're gonna have,
There's gonna be a lot of stuff.
there's a lot of stuff floating around. But what the pieces are, usually can still tell you what you were looking at. And so this is the part that always kind of felt like I was making stuff up to me. Because like, okay, well, what's something that has a mass of 15? It doesn't, now all of a sudden our rules for structures don't apply as well, because it's an ion. It doesn't have to have all carbons with 4 bonds. You can have a carbon with 3 bonds.
That's what it would seem like with the mass of 15.
Mass of 15 would be really nice.
CH3.
A CH3,
Yeah.
so there are certain characteristic numbers that show up all the time. So CH3. So a methyl radical, or sorry, a methyl cation is gonna show up with a signal of 15. What could 27 be? Or 29? 29 is gonna be an ethyl. Right, CH2, CH3, and we're just adding up the charges, or sorry, adding up the weights. So 12 plus 12 is 24, plus another 5 for the hydrogens. Yeah, because they basically are. If you can draw us, and it helps if we know what we started from, right? Because we can look at this and chunk it up like that, right? Oh, okay, that makes sense.
What's going on with the 27 then? It's like, it would be like C2H3, right?
It could be C2H3, but that doesn't seem like that's super stable, right?
So like what is? That's like a pretty prevalent line.
It is a pretty, so the amplitude here is what's called relative abundance, which basically you can tie to how stable it is. The more stable an ion is, the more likely that your Lego plane broke up that way, right? If the wing of your airplane is built really solidly, then no matter how many times you hit it with a golf ball, the wing is always
gonna be 100,
the wing,
or
or
if you think
Yeah.
about it that way.
and basically the 100, this is an arbitrary number. We just pick the largest peak and call that 100, and we just rate everything relative to that. Yeah, so what could 27 be? It could be C2H3. But that wouldn't really make a whole lot of sense.
Right.
Could it be CH2, I guess? There's some other pieces, yeah.
Because that's 3 is 3 hydrogens plus all the 2 carbons that would add up to 27, I think, something like that.
It's all that's
The other thing you can do is, so whatever the largest peak that shows up, that's what's called the molecular fragment. Basically, that's the whole thing, just missing an electron. So that tells us right off the bat that our total molecular weight for the whole molecule is 72.
But what if we had multiple molecules in?
Then all of a sudden, it's really impossible to differentiate. Did that,
So usually with MS, you would want to just use one,
right,
like, one known molecule in the sample.
right. And that's true for all of ours too, right? If you try to take a
Right.
random Argo mix sample, it's gonna be a
It's
mess
gonna be a
too,
mess,
right?
yeah.
Because you're gonna get both of them superimposed on top of each other. So pretty much all of these, we're assuming that we can get a relatively clean sample. And that's why one of the biggest major breakthroughs in the last 20 years was basically the way that you can automate and set up these different instruments in series. Do a GC And then what comes out of the GC automatically gets fed into a mass spec. Because with the GC, you can be pretty sure that you separated everything out. If you've got 3 components, the GC's job is just to separate it out into 3 samples, which then each go into a mass spec. Or
So,
each go
yeah,
into a
if
net
you
model.
have those 3 samples going through the GC, they can get separated,
Yeah.
and each one can have its own
Exactly.
spectrum.
Exactly, because trying to interpret multiple spectra overlaid on top of each other is basically impossible.
So that's probably why you wanna use GCMS for multiple things, like if you're.
Or even if you're not sure that if it's 95% pure, that's still enough that 5% could really throw off your IR.
Like, for example, if you're taking. Like a sample of like an energy drink, like that has a lot of compounds in it.
Yeah,
You probably wanna use GCMS like
separate them out first and then analyze it, yeah.
So, in the beginning here, we got to, methyl group is 15, right?
Mhm.
The full molecule 72. And we just assume that this 57 is the rest of the molecule, and this, you know,
Say that again?
it's 57, there's 72 minus 15, so
Bingo,
to the rest of.
exactly.
So,
That's exactly why I started going here. If we don't know what 27 is, we might look at what's 72 minus 27. Because what's the rest of the molecule? If we don't know what the 27 is. But we can look at, if we know that it adds up to 27 plus something, adds up to 72.
Do
I see what, this,
Yeah.
I'm just making stuff up.
It is, that's why this one felt, learning this before IR and NMR, this really was like out of left field. I struggled with this hard.
I'm glad that we learned IR and NMR.
They're a little bit more predictable, right? So what is 72 minus 27? 45? Is there something in here we could get that gets us to 45? So 30
Maybe something with 3 carbons. Wait. Right. You'll fall through.
that? Is that 45?
Let's say 36, 37.
That's 42.
That's 42.
If all the CH3s get knocked off, we just leave the CH2 in the middle.
Yeah, that'd be a little unlikely because usually want to break as few bonds as possible.
Yeah.
But then again, some weird things happen. There's rearrangements that happen while this is going on, right? You knock the electrons off and then it has to
So there
get to
could
the
just be
magnetic
some
field.
really like odd, unstable
Right.
rearrangement that somehow made it through.
But that's why we typically want to break as few bonds as possible because it's not going to go through multiple rearrangements usually.
It's just gonna go through like one
Right.
that just.
Let's say it's bombarded rather quickly. And
Right.
That's that.
The other thing is, if you want to treat these a little bit like IRs, and we don't try to take every peak on an IR and assign a bond to it, right? There's a lot of
Compared
stuff
to
we
an
can do.
NMR.
Right, NMR we try to assign everything, right? But
This is
IR,
kind of just showing you like pieces to the puzzle.
we can be really certain that that's probably an ethyl group, because
Yeah.
that makes a lot of sense that we're gonna have an ethyl group, same with the methyl group here.
I'm curious.
And same with 72 minus 15 gives us 57, right?
Then 57 minus another methyl group would give you the damn near that.
Right,
Close to it.
close to
That's
it,
the
or
42.
or
Yeah, that's
57 minus this. 57 minus 29 gives us the 43, right? So basically, and what would be, if we could only break one bond to make a carbocation, what's the most stable type of carbocation? Tertiary, right? And then secondary? If we knocked this off, we'd be left with a secondary carbocation, which is relatively stable, right? And then this all has a mass of 43. Which is why it's got the highest peak, it's the most stable ion you can make. Other than
That makes.
just knocking off the hydrogen. Hydrogen, you don't usually just knock off a single hydrogen. Because those hydrogens are really small for starters.
Yeah.
You need something to accept that hydrogen if you're gonna do that. Hydrogen, carbon's more electronegative than the hydrogen, right? So if you knock the hydrogen off, the carbon would be negatively charged, not positively charged. And these are
It's
all about
probably gonna
finding
spontaneously
catalysts.
get back to the
exactly.
carbon.
So basically this, when we see these, you're not trying to assign meaning to every peak. There is an explanation for every peak, but it might be convoluted. Look for the ones that are most obvious. Oh, there's a methyl here, but there's an ethyl there. There's a peak that looks like the mass minus a methyl. That means that there's probably a pretty easy methyl. If we just knock the methyl off, we get a secondary carbocation again, right? Also relatively stable. So we just did that. That gives us our 57, right?
So why is it that the 57 peak so high, why is it 15 peak so low? Because I don't think they'd be pretty similar.
So the way that these fragments work is that one of the pieces winds up taking the free radical, the unpaired electron, and the other one ends up with a positive charge. So when this splits, you get a methyl radical and a carbocation, a secondary carbocation. And radicals follow the same rules for stability, like a methyl radical is less stable than primaries. It goes primary, methyl, primary, secondary, tertiary again. But it's a bigger deal to have a full charge. So you're going to make more stable carbocations and less stable radicals for the most part.
That makes sense.
So when we do this, most of the time, the 57 fragment keeps the charge and the methyl gets the radical. But some of the time it goes the other way. And the methyl keeps the charge and the 57 is a radical. Right?
It's like filtering water then with 4 different layers of filter, so you have rocks and then the same.
Right, exactly. There's levels of complexity here for sure. And really, like mass spec is pretty useful if you have an idea of what your compound could be. Because you know what your total molecule weighs. So remember, this is that molecular ion. This one, whatever has 100% abundance, we call the parent peak or the parent ion. Which I don't particularly like that term because I feel like those should be switched, but no, I'm not gonna redefine things from.
This isn't saying that the molecule is an ion, right?
It's saying, not when it's stable, it's saying that the largest fragment that you can find is going to be if you started from this whole thing, you just knocked off a single electron and everything else stayed the way it was. But if you do that, the next thing that happens is this is gonna fall apart.
Yeah.
And that's why we get the rest of these. And it depends whether we get this fragment or that fragment depends on which electron actually got knocked off, right? Because if you knocked off an electron between these 2 carbons, that's gonna break apart differently than if you knocked off the electron between these 2 carbons. Right, so there is some probability and statistics involved in this too. We're not that we're actually gonna do the math for it. But just as far as why we don't just get one ion, is because we're dealing with moles of molecules all at the same time, right? Not all of them are gonna react the same way. All right. So, and this is, we're walking you through some of the stuff we were just talking about. The largest peaks correspond to the molecular fragment breaking up. So looking at the difference between the molecular ion peak and other peaks tells you what left. So that's exactly what you said. When you said, oh, well, that's a difference of 15 between those two. So the difference between those is you lost an ethyl. The difference between 72 and 43 is you lost an ethyl. Right? And those are going to be some of the most common things, especially if you have a bunch of methyl groups that could leave. It's going to be one of the more common ways that you can do that, especially if you have a methyl group that can leave and leaves you a secondary carbocation. As opposed to if this methyl group leaves, we get left with a primary carbocation. That's a little bit less stable, right? So we think this 57 peak is going to be predominantly either this carbon leaves or that carbon leaves. They're identical chemically, right? 43 leaving corresponds to, or 43 being left, means basically we knocked an electron off between these two carbons. The ethyl fell off and took the radical, and this chunk is left. Right, so that's gonna be our most common fragment, because instead of getting a methyl radical, you get a primary radical. And instead of getting a primary carbocation, you get a secondary carbocation. So that's about as stable as we can make this. If we have to break it up into a radical and a carbocation, a secondary carbocation and a primary radical, you can't really do any better than that with these carbons, right? Which is why it's the parent peak, why it's the most common result. Because whether you started by knocking that electron away or it went through some rearrangements in the process, that gives you the most stable pieces. And we haven't really defined radicals too much, but it's basically just a dot that you use it. That carbon doesn't have a charge, but it also doesn't have a full valence. It has an unpaired electron. And so we represent that with a dot. So those pieces are going to be our most stable pieces out of this molecule. And if you switch those two, we get something that's relatively similar too, right? 29 for our charge, which would leave a radical on this piece instead. And then 27, and the abundance would shift would be, and that's why we see the difference in the abundance is it's more important to keep the charge as stable as possible. But that's probably what this 27 is. It's just some other rearrangement that happened on the way to getting here.
Yeah.
And so it's a little bit tricky, and I'm not an expert in mass spec. That still confuses me sometimes. So, I'm not going to go too much into detail. The main thing is you don't have to be able to assign every one of these. It's helpful to give you something, though.
Why are there such close differences, like 27 to 43 to 71, and
So that could be a proton transfer.
okay, right on, so that could be, the 27 could also be that, like,
2 proton transfers would be a little unlikely. Does that make sense? Because those have to be separate events, and so the odds of both of them happen, yeah, unlikely. It's unlikely because this is such a large peak. If it's unlikely, we expect it to be a smaller abundance as well. And here's just an example of how different compounds, even with the same formula, fall apart a little differently. So this is methylbutane versus pentane. They both still have their parent peak at 43. But in this case, the molecular ion is a lot higher. It doesn't fall apart as easily. Because there's no way for it to fall apart that doesn't give you a primary radical and a primary carbocation. No matter where you chop up pentane, you're going to get a primary carbocation and a primary radical.
Compared to methyl butane, you have that methyl there. And
Exactly.
it kind of
That gets us
few options.
exactly.
Split.
Exactly. So it's a subtle difference, right? And this is why the cheap machines that the TSA uses, which, and I'm no shade, these things are really expensive to get a really nice one. The production model that they put in every airport everywhere has a hard time distinguishing between that percent abundance and that percent abundance. So you get a lot of false positives with those just because of their resolution is not as high.
yeah.
But and we still see most of the same. Except our 27 is higher now, right? So what if so we came up with 27 could be C2H3, right?
C2.
24 plus another 3, right?
Yeah.
So it could be, and this is gonna have like multiple levels of rearrangement to get here. You could conceivably have that.
Just figured out where we get these numbers from.
It takes a little bit sometimes, right? So probably this is what we're doing. we would expect this to be a little bit less stable. Than a secondary carbocation. But it's. You know, it's the only reasonable answer to give us 27, right? And 27 seems to be a relatively important peak, given it's more prevalent than the 29. And probably you wind up with two smaller pieces. That are left over from this. Yeah, this is the middle section falling apart. But again, this is what I mean by it's a little bit, you know, hand wavy. If you can explain things like the M-15 peak. The M-15, that is we lost a methyl group, right? In this notation, the capital M represents the molecular ion. Right, so M-15, M-29, those are both important because they show that there's a methyl group you can easily knock off. Shows that there's an ethyl group you can easily knock off.
Sorry, like the 42, 41, are those hydrogens getting knocked off? Or how?
Probably, yeah. Because there's a lot of other things that wind up happening in here, and because we still didn't make anything stable, so it's still going to be in the process of trying to rearrange itself and react to become more stable. We're not giving it time to get all the way there, so we're kind of getting a snapshot of where it is in the process of trying to become more stable.
So it could be like something like the double bond, like we talked about, and then
Right.
it's like, yeah.
Something like that, exactly. The other thing to look at is, it's kind of hard to see. What is that?
An extra hydrogen on something?
An extra hydrogen or an extra neutron?
Oh, could be an extra neutral.
If any of our carbons is actually carbon 13 instead of carbon 12,
And since there is a small.
there's a
percentage
1% chance or so per
That
carbon.
it is.
Yeah.
Carbon 13.
So we call them the isotopic effects. There's a possibility, depending on what you're looking at, that there's gonna be something that weighs a little bit more. We don't, and that's it's the largest significant fragment, we call it molecular ion, and then there's the isotope option. Right to the right of that. And so that can actually tell us something about what's present. Because different atoms have different probabilities of those other isotopes, right? So carbon's about a 1% chance it's carbon 13. And so the larger your molecule, the more likely you have a carbon 13. Out of 5 carbons, that's roughly a 5% chance, right? It's a little bit more. But if you have 60 carbons, the odds that at least one of them is a carbon 13 is pretty large, right? Some of these other ones, so hydrogen, almost no deuterium naturally, 0.01%. So that's not usually going to throw things off. Nitrogen, oxygen, same thing, less than 1%. Sulfur is a weird one because you wind up with 4 isotopes. This one's probably not measurable. This one's, you're probably not going to notice it too much, but if you get we call it the M+2 peak. So the molecular ion +2. And it's roughly a 20-to-1 ratio.
Yeah, you're gonna
Then
maybe find.
that might be a way of saying, proving, hey, I'm pretty sure I've got some sulfur because I've got this M+2 that's a 20-to-1 ratio. Versus chlorine, where you also have an M+2, but it's at a 3-to-1 ratio. Right, so if you wind up with that, with an extra peak right here, that is a third the size of the major peak. That's a better indication that there's chlorine in there too. Right, and then it's off the bottom of the.
And bromine.
Bromine's really obvious because you get two matching molecular ion peaks that are the same height. But separated because it's 50-50 roughly, right? So you wind up being able to see, so some of the isotope effects do explain some of those other weirdnesses that'll happen, but they tend to be relatively small unless you have a chlorine, a bromine, or a sulfur.
And they're usually found like all the way at the end at.
Those are the easiest places to see it. So here's an example of one. where we have two molecular ion peaks, basically, they're roughly the same height. And if they're roughly the same height, we'll just finish this thought, and then we'll finish up in lab, or you can take it home. If they're roughly the same height, and they're offset by 2, that's a pretty good indication that this piece has some bromine. Now, you don't see the M+2 anywhere over here though, right? Because one, what's the mass of the bromine? Just a single bromine by itself. 79, right? So anything that's less than a 79 on here can't have the bromine in it anymore. Basically, the bromine is one of the pieces that fell off. Right, but all these ones here, like. Let me zoom in over here so I can draw on the board. Like these ones, there's 2 that are separated by a difference of 1. And they're almost exactly the same height. That piece has bromine. I don't know what that piece is exactly, but it's got bromine. There's a few of them right around 79 and 81, right? That's probably bromine. That's bromine by itself. Maybe bromine plus an H. Maybe we have a hydrogen bromine positive charge. We had these two 79 and 81 could be bromine 79 with a positive charge and bromine 81 with a positive charge. These ones right here could be that. Because bromine typically forms bonds with hydrogens pretty readily, right? Yeah. So that's probably what this whole section is just bromine just by itself or with a hydrogen as your ion, but it's not very high. 43 is our highest. So what could it be? Let's finish this thought and then we'll be done for this section. What gave us a mass of 43?
What was it, the ethyl?
The ethyl was a methyl.
Yeah, it was the isopropyl, right?
Oh, the isopropyl.
So it might not be that exact structure. It could be CH2 here and a CH2 there, but this would be more likely because that was the positive charge on a secondary carbon. So if our most common fragment looks like this, missing a bromine, but we know that there had to be a bromine present, what's 43 plus 79? 122, isn't it? So what's a possible structure that would make a lot of sense? This, put the bromine on it. So probably this is CH3, CHBr, CH3. Because that adds up to 122 and 124, depending on if it's bromine 79 or 81.
It also kind of helps with the Heron P that you see that there is a positive charge, so there's something there that was more or less negative charge.
Exactly. This is the bromine is much more likely to hold on to the extra electron and get the radical. The carbon keeps the positive charge, be carbocation, because the bromine is more electronegative.
That's why you mentioned CH3, CH3,
It could be, it would still add up to the same masses, right?
Could there be like a small percentage of each? I mean.
Well, so we're making the assumption with these that I'm not going to give you a mixture of compounds, so we're treating it like it's a pure substance. As if we're trying to distinguish between these two, now all of a sudden that's where IR or NMR winds up coming in. If you have an NMR to go with this, it makes it really clear, just based on the number of signals, right? This is going to be 3 signals versus 2. So it's just another tool that we have. It's not something where I'm going to give you the mass spec and have you from scratch figure out. But if I give you an IR and a mass spec, you should be able to give me a couple of these suggestions, right? And that's what the lab is. Define some of the vocab and then do some practice with either ruling things out based on the mass spec, or here's an IR and a mass spec, give me a couple options. Right, and so I'll actually print these out for you, anybody who wants to just take it and take it home. That's totally fine today.
David's gonna come back and be like, shit, I didn't even leave.
I know,